Welcome to AI Paper Slop. Today we are looking at SPADE, which is short for self-play in adaptive synthetic executable environments.
Right.
This is by Yu and a really impressive team of researchers from UW, Stanford, MIT, and several other institutions.
Yeah, it's a huge collaboration.
It is. And I'm going to give you the core insight right up front. So the bottleneck for training agentic AI is no longer just raw text data.
Oh, definitely not.
Right. It is the supply of verifiable environments.
Yeah.
And SPADE basically solves this via self-play, where a single large language model plays two distinct roles.
Exactly.
It acts as an environment designer writing complete executable Python environments using the standard OpenAI Gem API, and it simultaneously acts as a reasoning agent that learns to solve them.
Which is such an elegant setup.
Right. And by optimizing for a metric they call hint-based regret, the model constantly generates diverse tasks perfectly targeted at its own learning frontier, which honestly paves the way for open-ended, continuous self-improvement, completely removing the limits of human-curated training data.
Yeah, and the timing of this paper is just, it's critical for anyone working in reinforcement learning right now.
For sure.
If you look at what the major AI labs are doing, they are hitting this massive roadblock when it comes to scalability. I mean, they are spending upwards of $1 billion a year just billing out their environment budgets.
$1 billion just on environments.
Yeah, because when you're trying to train an agent to take sequential actions, it obviously needs a world to act inside of.
Right.
But right now, whether those environments are, painstakingly hand-curated by human developers or maybe statically synthesized by some frozen generator, they're ultimately fixed pools.
Which means they suffer from the exact same problem as giving a student a single printed workbook.
Exactly.
Once the student masters all the math problems in that specific workbook, their learning curve just completely flatlines.
Yeah, they've exhausted the training signal.
Because the goal distribution is entirely static.
And that static nature is exactly what SPADE disrupts. They introduce this foundational shift code as environment.
Okay, break that down for us.
So rather than creating disparate APIs or relying on hard-coded text games, SPADE unifies all tasks into a single format. It forces the environment designer to output Python code that implements a full Markov decision process, or MDP.
Right, and for the engineers listening, an MDP requires defining states, available actions, transition dynamics, and a reward function.
Yeah, and SPADE maps that directly into a Python class.
Oh, wow.
It literally writes a hidden internal state, a reset function to initialize the observation, and a step function to handle state transitions, verification, and reward distribution.
I mean, if any computable Markov decision process can be written as a Python script, we aren't just giving the AI a math problem to solve anymore.
No, not at all.
We are basically dropping it into a custom micro-universe. It has its own physics, its own rules, its own multi-turn interactions. It's essentially a procedurally generated video game engine for LLMs.
That's a perfect way to look at it.
But I do have a serious technical hesitation here.
Oh, let's hear it.
We all know what happens when you ask an LLM to write complex Python code from scratch. It hallucinates variables, it creates infinite loops, or it just throws, basic syntax errors.
Oh, yeah. Standard LLM behavior.
Right. So if the LLM is acting as a designer and just outputting thousands of Python scripts, how on earth are we verifying that they are actually solvable, let alone useful, for training a multi-billion parameter model?
Well, that's the first major hurdle you have to clear if you're building a system like this. And SPADE handles it in a really rigid two-stage filter.
Yeah.
First, every generated environment goes through a strict deterministic validation phase, just for syntax and executability. And this happens before it ever touches the training pool.
So it actually runs the code.
Literally attempts to compile and run the Python class. If it throws a syntax error, or if the reset and step functions crash on just basic dummy inputs, it is instantly discarded.
Just thrown out.
Gone. The agent never even sees it.
Okay, so we can guarantee the code runs without crashing.
Yeah.
But, execution isn't the same thing as teaching value. Like, a script could run perfectly and just return a flat reward of 0 no matter what actions the agent takes, which teaches the model absolutely nothing.
Exactly. And that distinction is the entire mathematical engine of SPADE.
Okay.
To ensure these environments actually teach the agent something new, the researchers had to invent a way to measure the difficulty of a custom Python universe without having a human evaluate it.
Which is wild to think about.
It is. And they do this through a unique reward signal they call hint-based regret.
Let's really break down the mechanics of this, because I feel like this is where the self-play aspect really takes over.
Yeah.
How do we extract a difficulty signal using the model itself?
Well, it uses the exact same LLM weights.
Really?
Yeah, in the paper's main scaling experiments, they use the Qwen 330B backbone to act in both roles.
Got it.
So when the LLM is prompted to be the environment designer, it generates the executable Python environment, but, and this is key, it is also forced to generate a privileged hint.
A privileged hit. What does that look like?
This isn't just, a generic word of encouragement. It contains highly specific task-relevant information. It might be a partial solution, a specific search strategy, or maybe a key structural observation about the hidden variables in the environment it just built.
Ah, okay. So the designer builds the puzzle and simultaneously writes down a cheat code that theoretically solves the puzzle.
Yes. Then the system switches hats. The exact same LLM weights are now prompted to act as the reasoning agent.
Okay, here we go.
The agent is dropped into this newly generated environment and plays it twice in parallel rollouts.
Okay.
In one rollout, it is provided with the privileged hint. In the other rollout, it has to navigate the environment entirely blind.
I see. And the difference in performance between those two rollouts becomes the training signal.
Exactly. The reward function for the environment designer is formally defined as the agent's average reward with the hint, minus the agent's average reward without the hint.
Oh, that's clever.
Yeah, that gap is the hint-based regret.
So you essentially end up with three possible outcomes, right? Like three distinct regimes.
Yeah, walk through them.
Okay, regime 1. The regret is low because the agent succeeds in both rollouts.
Yeah.
That tells the system the environment is too easy. The agent has already mastered this skill and didn't even need the hint.
Spot on.
Regime 2. The regret is low because the agent fails in both rollouts.
Right.
Which means the environment is either broken, structurally impossible, or so far beyond the agent's capabilities that even the cheat code couldn't save it.
Exactly. Which leaves the third regime, which is the absolute sweet spot for reinforcement learning, high regret.
Okay.
The agent succeeds when it has the hint, but completely fails without it.
Wow, okay.
That tells the system, mathematically, that this specific Python environment is resting precisely on the learning frontier. It is demonstrably solvable because the hint proved it, but it currently requires reasoning steps that are just out of reach for the baseline agent.
I want to ground this in a real example from the paper so everyone can picture what this looks like in practice.
Yeah, that helps a lot.
There is this generated task called the pre-emphasis de-emphasis signal lab.
Oh, that's a great one.
Yeah, the reasoning agent is dropped into a noisy analog channel environment, and its goal is to restore high-frequency audio clarity. To achieve this, it has to balance two interacting audio filters.
Right.
So when the agent attempts this without the hint, it just flails.
Wow.
Over 12 sequential turns, it analyzes the spectrum, it identifies the severe loss, enables the filters, but then it essentially guesses a value of 5.0 for the pre-emphasis filter.
Just a blind guess.
Totally. It completely fails to hit the target clarity metric, times out, and gets a partial reward of just 0.3 where.
But look at what happens when that same agent plays the same environment with the privileged hint.
Right.
The hint the designer generated explicitly states that the filters need to be inversely related to the high-frequency channel loss, and it suggests starting with the value around 1.0 to 3.0.
So it gives it the structural bounds.
Exactly. And armed with that structural knowledge, the agent's behavior is totally transformed. It doesn't guess 5.0. It methodically tests 2.0, analyzes the environment's feedback, adjusts both filters to 2.5, transmits the signal, and hits the target clarity in 11 turns, scoring a perfect 1.0 reward.
The math there is so clear. 1.0 minus 0.30 leaves a hint-based regret of 0.70.
Yeah.
So the environment designer gets a massive reward update for generating that specific task because it successfully found a vulnerability in the agent's current reasoning capabilities.
Exactly.
If you think about the physics of this, it is exactly like having a highly skilled spotter at the gym.
Oh, that's a good analogy.
Like if you used a purely adversarial reward function where the designer just wants the agent to fail, the designer would load 1,000 pounds on the bench press.
Right. Impossible.
The agent gets crushed, learns absolutely nothing, and the gradients collapse. But if you use a purely cooperative reward, the spotter just lifts the bar for you.
And again, zero muscle is built.
Exactly. Hint-based regret forces the spotter to put just enough weight on the bar to stimulate muscle growth, while mathematically guaranteeing it is physically liftable by the agent's current musculature.
That spotter analogy really highlights why constrained competitive dynamics are so crucial in multi-agent RL. You are anchoring the curriculum to what the agent can actually achieve at that exact moment in training.
Right.
However, solving the difficulty problem introduces a secondary, arguably more dangerous challenge for anyone trying to scale this up.
Oh.
Yeah. Your LLM can now generate perfectly difficult tasks. But what stops it from generating the exact same perfectly difficult task over and over again?
Ah, right. If my gym spotter figures out that bench pressing 225 pounds gives me the mathematically optimal workout, they might just have me do that every single day.
Yeah.
I'd end up with a massive chest and completely neglect my legs. The agent would overfit to a tiny slice of the problem space.
And in the literature, this is classic mode collapse. The authors of SPADE refer to it as the invisible leash of self-play.
The invisible leash.
Yeah, when an LLM is optimizing a reward function by only conditioning on its own internal weights and its previous outputs, it inevitably narrows its generation distribution.
It gets lazy.
Basically. It finds a local optima of high-regret tasks and just camps there. The paper actually ran a control experiment without any external grounding to test this.
What happened?
The environment designer found a rotating maze navigation task that yielded high regret, and then it proceeded to generate that exact same task 41 times in a row.
41 times.
It just slightly varied the grid layout and the wall placements. The entire training stream collapsed into a single narrow task family.
I mean, if you were trying to train a generalized reasoning agent, that is a catastrophic failure mode.
Absolutely.
You'd spend millions of dollars in compute just to create an absolute master of rotating mazes who fails at basic arithmetic or like standard API calls.
Exactly.
So how does SPADE break this invisible leash to ensure continuous open-ended diversity?
They break it using two overlapping mechanisms, which are corpus grounding and environment memory.
Let's start with corpus grounding.
So corpus grounding is how they inject real-world breadth. During generation, the environment designer is conditioned on documents sampled randomly from massive pre-training corpora.
Okay, so it pulls in outside text.
Yeah. For the math and science environments, they sample from 10,000 documents in data sets like DCLM and Megascience.
Wow.
For the software and tool use environments, they sample from 15,000 code documents from the Nematron corpus.
So every single time the designer is asked to build a new environment, it's looking at a freshly sampled piece of human knowledge.
Exactly. It might be a dense physics forum post, an obscure API documentation page, or an excerpt from a biology textbook.
I want to clarify something here, because if you were designing RL pipelines, this distinction is crucial.
Yeah, definitely.
When you say the textbook documents are used in the environment, you're not saying this is an open book test for the reasoning agent.
Oh, no.
The agent isn't reading the physics textbook during the episode.
No, the reasoning agent remains entirely blind to the raw corpus document. Only the environment designer sees it.
Okay, that makes sense.
The designer reads the textbook excerpt, extracts the core concepts, and uses them as raw material to program the physics, the hidden states, and the transition rules of the Python environment.
I see.
The external corpus supplies the vast breadth of the world, pulling the LLM out of its own internal biases.
So corpus grounding gives you the breadth. What is the role of the environment memory?
While the corpus dictates what the environment is about, the environment memory dictates how hard it should be relative to the agent's history.
Ah.
SPADE maintains a cross-episode memory buffer of past environments. Crucially, these environments are annotated with their historical regret scores and their skill tags.
So it remembers what worked.
Yes. Instead of starting from a blank prompt every round, the environment designer is fed high regret seeds from the memory buffer to mutate and expand upon.
Oh, that's smart.
It is also fed too easy or too hard examples with strict instructions to actively avoid them. This ensures the designer doesn't waste compute reposing challenges the agent mastered 100 steps ago.
For the engineers tracking this, you're probably wondering if we have actual metrics to prove this prevents mode collapse, rather than just anecdotal claims.
The data on this is definitive, and they measure it using the Venn score.
Right, the Venn score.
For those unfamiliar, measuring diversity in code generation is notoriously difficult. You can't just use exact match metrics because a single changed variable name makes the code technically distinct, even if the underlying logic is identical.
Yeah, it would just fool a basic text comparison.
Exactly. So the Venn score solves this by looking at the eigenvalues of the code embeddings. It essentially measures the linear independence of the feature vectors in the embedding space to calculate the effective number of truly distinct items.
Basically, it's checking if the environments are actually covering new semantic territory, rather than just clustering in the same exact spot.
Exactly. So for a batch size of 24 environments, the mathematical ceiling for a perfectly diverse, uniformly distributed sample is a Venn score of around 21.3.
Okay, 21.3 is the ceiling.
Throughout the entire 400-step training run, SPADE's Venn score holds completely flat at 21.0.
Whoa.
Yeah, it practically hugs the absolute mathematical ceiling.
That's incredible.
And to prove the necessity of Corpus Grounding, they ran an ablation study where they removed it.
I bet that dropped.
It collapsed massively. Using their per 100 batch metric, the diversity dropped from 0.68 all the way down to 0.04. The generation stream just flatlined into identical tasks almost immediately.
So we have the Python micro-universes, we have the difficulty tuning through hint-based regret, and we have mathematically proven infinite diversity through corpus grounding and memory.
Yeah, all the pieces are there.
So when you let this entire system run at scale, what actually happens to the AI's capabilities?
You witness the emergence of a natural dynamic curriculum.
Which is the dream, right?
Truly. Because the environment designer is constantly probing for that high-regret sweet spot, the tasks organically evolve in complexity as the reasoning agent gets smarter.
The paper has a great breakdown of this.
The researchers track this evolution beautifully, detailing the qualitative leap from step 0 of training to step 384.
Yeah, if you look at the early training phase around step 0, the tasks are relatively straightforward. The designer builds environments like a car ownership dispute legal forum, or maybe an introductory thermodynamic lab.
Simple stuff.
Right, because in these early stages, the agent hasn't developed complex deduction skills. So the environment designer essentially hands the agent the required knowledge.
Literally hands it over.
Yeah, the actual physics formula needed to solve the thermodynamic problem, like the formula for relativistic mass, is just literally printed in the opening observation prompt. The agent simply has to parse the text, identify the formula, and apply it to the visible variables.
But as the agent trains, it rapidly optimizes for that pattern. Parsing a formula from the prompt becomes trivial.
Right.
The success rate without the hint goes up, which means the hint-based regret plummets. The environment is now firmly in the too easy regime.
So the designer has to pivot.
Desperately. To maximize its own reward, it has to adapt and find a new way to challenge the agent.
And this leads to what happens at step 384, which frankly blew my mind.
Oh, by step 384, the tasks become staggeringly complex. The environment designer outputs a thermodynamic cycle manipulation lab.
Same domain, entirely different beast.
The Python code for this single environment balloons to 376 lines. It implements 19 different hidden state variables.
Wow.
But the most fascinating shift is structural. The physics formula is no longer provided in the opening prompt.
The designer basically locked the instructions behind a security protocol within the environment itself.
Yes.
The opening prompt just gives the agent a generic set of instruments like activate heating, initiate expansion, measure entropy. The agent now has to engage in multi-step tool use, querying the environment and exploring the hidden state just to find the governing rules before it can even begin to attempt the ultimate goal.
I mean, SPADE naturally created the concept of hiding the formula.
That's insane.
No human engineer ever wrote a hard-coded rule that said, hey, once the agent reaches step 300, make the tasks harder by hiding the instructions.
Right.
The system organically discovered that state-gated interaction, forcing the agent to dig for information over multiple sequential turns, was the only mathematical way to extract hint-based regret from an increasingly intelligent reasoning agent.
That is the raw power of open-ended coevolution.
Yeah.
You don't have to predict how the agent needs to learn. The system discovers the optimal curriculum path autonomously.
Exactly.
And we can see this translated directly into the scaling benchmarks.
Yeah, so to train the policy, the researchers used GRPO, or Group Relative Policy Optimization.
Right, which is huge right now.
For the technical listeners, you likely know that traditional PPO requires a separate value model to estimate the baseline for advantage calculation, which is incredibly memory intensive for 30 billion parameter models.
Yeah, it just chokes the compute.
GRPO bypasses this by sampling a whole group of outputs for the same prompt and normalizing the advantages within that specific group. It's highly efficient and scales beautifully with these generated environments.
Let's look at the concrete numbers on those benchmarks. How does SPADE compare to the traditional method of training on fixed pools of environments?
The contrast is stark.
Yeah.
When you train an agent on a static, fixed pool of environments, the model quickly memorizes the distribution. The fixed baseline saturates early, yielding only about a plus 1.2 average improvement across the board.
Ouch.
Yeah, the learning basically stops. But SPADE scales continuously. At the 30 billion parameter scale, SPADE yields a plus 8.1 average absolute gain across 8 heavily tested, held-out benchmarks.
Plus 8.1 is massive.
And keep in mind, these are totally unseen tests covering competition-level math, advanced science reasoning, and complex coding tasks.
Well, the single most impressive metric to me is the tool use benchmark. Because multi-step reasoning and tool orchestration is really where agentic AI is being pushed right now.
Oh, definitely. On the ACEBench-Agent tool use benchmark, SPADE delivers a staggering plus 13.9 gain at the 30B scale.
Wow.
The implication here is profound. It proves that dynamically generating executable Python environments doesn't just improve like single-turn mathematical reasoning. It fundamentally upgrades the model's ability to navigate complex sequential tool use scenarios.
Because it's been practicing inside these little puzzle boxes.
Exactly. By forcing the agent to constantly interact with novel state-gated Python classes, you are building an incredibly robust capacity for autonomous exploration and tool integration.
Okay, so let's summarize the key takeaways from the sources we've unpacked today. SPADE basically takes environment design, which is currently a static, multi-billion-dollar human bottleneck, and transforms it into a dynamic, learnable component of the reinforcement learning pipeline.
Perfectly said.
By having a single underlying model play both the environment designer and the reasoning agent, and by driving them forward with the elegant math of hint-based regret, the system naturally builds an ever-expanding, perfectly tuned curriculum of Python microuniverses.
Furthermore, well, not just that, but by anchoring that generative process in real-world corpora and maintaining a strict cross-episode memory buffer, SPADE completely avoids the pitfalls of mode collapse.
Right, the invisible leash.
Yeah. It ensures the agent is perpetually pushed into new domains of knowledge and new dimensions of structural complexity, rather than just endlessly refining a single narrow skill.
Which brings me to a final thought for you to mull over as you look toward the future of model training.
I like where this is going.
We constantly hear industry analysts warning about the impending data wall.
Oh, all the time.
Right. That terrifying theoretical moment when the tech industry finally exhausts the supply of high-quality human text to train our models on. But if SPADE proves that models can programmatically design, strictly validate, and dynamically scale their own increasingly complex micro-universes to train inside of, is the data wall actually an illusion?
That is the big question.
If the models can build their own infinite curriculum, are we already looking at the beginning of true, open-ended self-improvement?